Okay, for this video, we'll be going through your work energy power question 2. Okay, so a stone of mass 0.4 kg, please annotate. So this is my mass. So I call it M, and because everything must be in SI unit, this is okay. So if it's in grams, always change it to SI unit of kg. Now it is launched vertically upwards from a slingshot with an initial velocity of 10 meter per second. So this is the V. So if it is launched with an initial speed of 10 meter per second, that means it already has speed. So if it has speed, therefore it has energy in the kinetic store as it was launched. Okay, so part A, explain how the principle of conservation of energy applies as the stone is launched. So principle of conservation of energy is a definition or principle that you need to memorize. Okay, so it is, let me write it here. Okay, so this is the principle of conservation of energy. It states that energy cannot be created or destroyed and can only be transferred from one store to another. Okay, the next sentence is also important. The total energy of an isolated system is constant. So what they are trying to ask us here is that how will the principle of conservation of energy apply as a stone is launched? That means we must talk about energy being transferred from one store to another. This is the first point. And the second point that must be in this explanation is that total energy of an isolated system is constant. So let's see what is the answer. Okay, so the answer is this. When the elastic band is released, energy in the elastic potential store, right, this is actually transferred from the user of the slingshot to the elastic band. Okay, energy in the elastic potential store of the slingshot is transferred mechanically. So you actually need to talk about the pathway, right? Because you are pulling the object at a distance, you are applying a force, and the object moves in the moves a distance. So this is by mechanical way. Okay, it's transferred mechanically to the kinetic store of both the slingshot and the stone, right? Because the slingshot will also be moving, the stone will also be moving. Therefore, if they are both moving, there are energy that is being transferred to the kinetic store of both the slingshot and the stone. So it is very important to write who possesses all this energy, whose store is the energy being transferred to. Okay. So after that, because the story is about the stone, as the stone rises, energy is transferred mechanically from the kinetic store of the stone to its gravitational potential store. Okay, it's still within the stone, but it is transferred from kinetic store to the gravitational potential store. Okay, however, because it's moving in air, some energy is also transferred to the internal store of the surrounding due to air resistance acting on the stone, right? Because we have to do work against air resistance. And I must say again, air resistance is not energy, it is a force. So we need to do work against this opposing force. Okay, so this is talking about the transfer of energy from one store to another, which was the first point in our principle of conservation of energy. Then we need to apply the second concept, which is the total energy of an isolated system is constant. So how do you write it? Throughout, the total energy of the system, right, which actually consists of the slingshot, the stone, and also the surrounding remains the same. So for this question, it only involves the slingshot, the stone, and the surrounding. So this is our isolated system. Okay, and we must just add in this statement that the total energy of the system remains the same. So this is how you write your answer to show how principle of conservation of energy is being applied. Okay. So now for some calculation, calculate the energy of the kinetic store, right? So I'm looking for EK when it was initially launched. So what were the information that was given? The mass M is 0.4 kg. Let me check. Yes, 0.4 kg. Then initially there was a velocity or speed of 10 meter per second. So let us apply into this formula. EK equals to half mv square. So equals to half. The mass is 0.4. The V is 10 and we need to remember to square it. So the final answer will be 20.0 joules. Okay, take note that the SI unit for energy is joules. Okay, so this is quite simple. Now we assume that for part C, air resistance is negligible, so we calculate the maximum height that it can be reached. Okay, so we were doing this just now. The energy in the kinetic store of the stone will be transferred mechanically to the gravitational potential store of the stone. That means by applying my principle of conservation of energy, okay, by principle of conservation of energy, my EK will be equals to EP, the gravitational potential energy. Okay, but this is by assuming that air resistance is negligible, because we know that if it moves up against air, then there will be some energy that's transferred to the internal store of the surrounding. But now we ignore that first. Okay, we just want to find hypothetically what is the maximum height that it can reach. So EK we have calculated is 20. Okay, so what happens if in the exam your part B is wrong? Okay, you can still get marks error carry forward marks. Okay, if you apply your principle of conservation of energy correctly and your formula is all correct. Okay, so always continue doing it. So this is equals to mgh. We want to actually find our h. So 20 equals to 0.4 times 10 and h. Therefore, my h, if I do my calculation, will be equals to 5 meters. Okay. Now, the stone is brought to the moon and launched vertically upwards with the same initial velocity. That means the initial velocity is 10 meters per second. But what has changed is that on the moon, the g of the moon is actually just 1.6 Newton per kg, less than that of Earth. Now we want to calculate the maximum height. Okay, so again, if it has the same velocity or same speed, that means its initial kinetic initial energy in the kinetic store is going to be 20 joules. It's going to be the same. Okay, so let us repeat this by principle of conservation of energy. So equals to EP, so 20 equals to mgh. But now we need to take note that the mass of course remains the same, right? The g is now 1.6 and the h is the one that we want to find. So with that, my h will be, if I calculate out, it will be equals to 31.3 meters. Okay. Okay, I'll go on to do question 3. Okay, question 3 actually shows a roller coaster initially at rest. Now, this is important. This tells me that initial velocity is 0. And therefore, no kinetic energy. No energy in the kinetic store. However, I recognize that there is a height above ground. So this is going to be my h. Okay, and if it has such a h, then there's going to be gravitational energy in the gravitational potential store. Okay, so which I can find. And I recognize that this height is actually the highest. That means the energy in the gravitational potential store is the maximum. Okay, there is no mass given. All right, there's no mass given, so why don't I call it mass m? And of course, if there's no accident, the mass should be the same, right? No one falls out of the roller coaster, the mass should be the same. So the mass at every point P, Q, and R is going to be the same. Okay, so don't worry. They want us to calculate the speed of the roller coaster at position P, Q, and R. So let's do P first. At P, we find that there is no height. The height is 0. And if we were to ignore air resistance and friction, okay, so this one means no friction, and let us ignore friction, ignore air resistance, okay, then I can find the maximum speed reached by the roller coaster at point P. Okay, so at the initial point, the EK is 0, right? Because there's no speed, it wasn't moving at first, but there is maximum energy in the gravitational potential store. This is opposite of P. At P, it actually has maximum energy in the kinetic store, but because it doesn't have any height, the energy in the gravitational potential store is 0. So let us calculate the EP at initial. Okay, EP at initial. So it is equals to mgh, and because I don't know what is m, I'm going to leave it as m. The G is 10, is happening on Earth, and this is 16.2. Okay, so this is going to be 162 m. Okay, there's no EK, so let us now go on to calculating the EK at position P. Okay, so take note of my notation. This is energy in the kinetic store of P, and this is going to be equal to the energy in the gravitational potential store at initial. Okay, so this is going to be half mv square equals to 162 m. Okay, since the mass remains constant, I can actually cancel this part out. So if I work out, v square will then be equals to 318. Okay, 314. Okay, let me do my calculation. Okay, sorry, my mental sum not very good. V square should be equals to 324. Okay, that means V at P is going to be square root 324, and that will give me a value of 18 meter per second. Okay, so actually I'm applying principle of conservation of energy, right, for my to find the speed of roller coaster at P. Now I'm going to do the same for Q. Okay, so at Q, I know it's going to have some energy in the gravitational potential store. Okay, because it has a height. So I can actually calculate it out now, equals to mgh, and m I keep it constant. G is 10, the height is 11.2. Okay, but I don't know what is the speed at Q. So I would not know the energy in the kinetic store at Q. Okay, so now I have to apply my principle of conservation of energy. I apply principle of conservation of energy between initial and at Q. So initially I have this amount of energy, 162 m, correct? Because at initial I only have energy in the gravitational potential store. Now applying principle of conservation of energy, this must be equals to the energy at Q, the total energy at Q. And the total energy at Q consists of EPQ because it has height and EKQ. Alright, so I've already calculated out what is EPQ. EPQ is actually 112 m, right? 112 m. But I don't know what is EKQ. So now I do my math. EKQ is actually equals to 50 m. Now what is the formula for EKQ? It's actually half m v square, and this v is the velocity at Q, equals to 50 m. And since my m and m actually appears on both sides and is constant, nobody fell out, so I can calculate my VQ square to be 100. Therefore my VQ will then be equals to 10 meter per second. Okay, so you notice that the speed at Q is lower than the speed at P, because some of the energy, since it traveled to P and to Q, some of this energy has been transferred to the energy in the gravitational potential store. Okay, so now I'll do it one more time for R. Okay, so R, I see that there is actually a height of 9 meters. So I can calculate E P R, okay, gravitational potential energy at R to be mgh. This is the formula. M remains unknown. G is actually 10 and H is now 9 meters. Okay, so this will be 90 M. And again, because I don't know the speed at R, I'm not able to calculate the kinetic energy at R. Okay, so this is what I'm going to find out. Then again, I apply my principle of conservation of energy, and I'm going to take the initial value, which is 162 M, to be equals to EPR plus EKR. Okay, and since I already found my EPR to be 90 M, then I can actually find my EKR to be equals to 72 M. Yes, and EK formula is half mv of R square 72 M. So again, M and M can cancel. So VR whole thing square is actually equals to 144. Okay, therefore my VR is going to be 12 meter per second. Okay, so this is how you solve this. You always need to apply your principle of conservation of energy. You always have some values to start off with, and this value of the initial energy will be same throughout the system. Okay, it's just being transferred to other parts. Can? Okay, I'll be going through question 4 now. Okay, so question 4 is sort of like an explanation question. There should be no calculation to it. They want us to describe the useful energy transfers that takes place when a modern flashlight containing a solar panel and a lithium-ion battery. So this is by electricity, by electrical source. Okay, energy received from the sun is stored in the battery, right? So it's going to be stored as chemical potential energy. Okay, describe the useful energy changes that take place when a flashlight is being charged under the sun. So if it's charged under the sun, and of course the flashlight is not being used, so it will be taking the sun's energy, okay, and then it will be storing it in the inside the lithium-ion battery as chemical potential energy. So how do I answer this? Okay, energy is transferred by the propagation of electromagnetic wave. Now, what are actually electromagnetic waves? We haven't really learned it yet. You will learn it in the subsequent chapters. So this is actually a wave that coming from the sun. And these electromagnetic waves actually consist of our UV light ray, our visible light. That's how we can see things when the sun rises. And there's also infrared radiation. There are altogether 7 sections of these electromagnetic waves. We'll go through later on, but now you just need to know that this energy is transferred from the sun by this propagation of electromagnetic waves. So this is actually the method, okay, the way of being transferred, and this energy is then transferred to the internal store of the solar panel, internal store. Okay, then this energy is further transferred electrically. So again, this is the method, the pathway from the internal store of the solar panel to the chemical potential store. Okay, so this is what the battery will store the energy as in the chemical potential store. Okay, so this is when the flashlight is being charged under the sun. Now, when the flashlight is being switched on at night, so of course you'll be using the energy in the chemical potential store of the battery. Okay, so this is the answer. Energy is now transferred electrically, so this is the method from the chemical potential store of the battery. Remember, that was where the energy was being stored. It was being stored as a chemical potential energy. Okay, so this energy is transferred electrically from chemical potential store of the battery to the flashlight, which then emits the light and infrared waves to the surrounding. Okay, therefore this is actually transferring the energy to the internal store of the surrounding. It went out of the flashlight, it went out of the battery to the flashlight, and then it got transferred to the internal store of the surrounding. So you always try to write down the method, the pathway, the transfer pathway, and also the store. And with the store, how the energy is where the energy is being transferred, you need to identify the owner of the store. Okay, so I'll be going through question 5 now. Question 5, we again switch to calculation question. Okay, so for question 5, it shows a trolley with a mass of 4 kg. So again, annotate, let it be M, and it is 4 kg, so we don't need to change it. It's already in SI unit. So it was initially at rest, that means the speed was 0. So if it's 0, that means the energy in the kinetic store is 0. So this one is at position A. Okay, so when the trolley is released, it moves towards position B, C, and D. At position D, it moves up to a maximum height of 2 meters. So if it has height, then there's going to be energy in the gravitational potential store. And then it moves down, roll back to C. Now take note that both AB and BC are smooth surfaces, but there's friction along CD. So there's going to be friction along CD. A, B to C is actually smooth. So they want us to calculate the energy of the kinetic store of the trolley at position B. Okay, so let us compare the different types of energy at A and B. At A, the kinetics energy in the kinetic store is 0, but it's going to have EP. Okay, energy in the gravitational potential store, and actually I can calculate it now because it's mgh. I have mass of 4 and g is 10 and height of 2.5, so it will be actually 100 joules. Okay, so they want the energy of the kinetic store of the trolley at position B. At B, there is no energy in the gravitational potential store because it's at the lowest height, so it is 0. So how about the EK? So the EK, by principle of conservation of energy, okay, the EP at A is going to be equal to the EK at B. Okay, so this is of course ignoring air resistance. Ignore effects of air resistance. And since there's no friction, right, so all this energy from A, which actually only consists of energy in the gravitational potential store, will then be transferred to the energy in the kinetic store at B. So it is equals to 100 joules. Okay, so with this, then I can calculate the speed of the trolley at position C. Okay, at position C, because this is frictionless, it is smooth, so, and because it's at the same height, the EP is also 0. So the EK at B is going to be equal to the EK at C. So it is going to be equals to 100 joules. And EK at C, I can actually do my half mv square equals to 100 joules. So I do my manipulation. V square will be equals to 50. So my V is going to be 7.07 meter per second. Okay, so you plug in the value of M, K, then you get this V square equals to 50, and finally the answer is 7.07 meter per second. Okay, now they want us to state the energy transfer that occurs as the trolley travels from C to D. So from C, there is no height, to D, there's actually height. But we also take note that from C to D is actually having friction. So it has to do work against friction. So actually some of the energy is going to be transferred to the surrounding as internal energy. Let's see how to answer. Okay, energy from the kinetic store of the trolley at C is transferred mechanically to the gravitational potential store of the trolley at D because there's a height. Okay, and when the trolley reaches the maximum height, the velocity is 0. So all of this kinetic energy in the kinetic store is transferred to the gravitational potential store of the trolley. But because there's friction, so some of it is actually transferred to the internal store of the trolley. The trolley is also going to be heated up, right? Internal store, and also to the surrounding. This is due to work done against friction. Okay. So now let's calculate D. Hence, assuming that there's constant frictional force along surface CD, calculate this frictional force. So this is a little bit complicated because at C, the amount of energy that it has is 100 joules. Okay, this is actually in the EK, kinetic store of C, right? Let us compare with the energy at D. At D, okay, the V is 0, right? That means the EK is 0. But because at D, there is a height of how much? Height of 2 meters. Okay, height is 2 meters. Therefore, the energy in the gravitational potential store is going to be, I do a quick calculation, 4 times 10 times the height of 2, it will be 80 joules. Oh, look at the difference. Okay, the total energy at C is 100 joules. Total energy at D is 80 joules. That means there is a difference of 20 joules. Difference of 20 joules. Where did this 20 joules go to? It is used to do work against the frictional force at D. Okay, do work against friction. Okay, and remember, work done formula is force times distance moved. The force is what we want to find. The work done is 20 joules. How about the distance traveled? The distance traveled is actually 2.5 meters. Take note, it should be 2.5 because the frictional force is acting in this direction. So we should take the distance that is also in this same direction. Okay, we should not take 2 meters. So F times 2.5, and therefore my F is going to be 8 Newton. Okay, take note that this is the average frictional force. Alright. So after being momentarily at rest at position D, okay, the trolley rolls back down to position C. Okay, if it rolls back down to position C, that means it's going to encounter another round of friction force. Okay, so they want us to calculate the speed of the trolley when it returns to C. So if it's going to roll down from D to C, okay, and there being friction, it's going to do work against the frictional force, and the frictional force is going to be the same. Therefore, the work done against frictional force is going to be 20 joules. So at D, initially it had 80 joules. We calculated, right? So now let us calculate what is the energy available at C after it went down. So you should take 80 minus 20, we get 60 joules. So this is the energy that it has at C. At C. Okay. At C, because it doesn't have any gravitational potential energy. Okay. So this is going to be the energy in its kinetic store. So 60 joules equals to half mv square at C. So we do our calculation again. Our C speed is going to be 5.48 meter per second. Okay.